And we enjoy visit now of Anne from Gdansk. She is in Gdansk at University of Gdansk at International Center for Theory of Quantum Computing. And today she will tell us about quantifying non-classicality via local operations and sheer randomness. Yes, go ahead.
Okay, thank you very much for the introduction. I think I might try to use my cursor here.
Okay,
to...
yes, so you don't need this. Okay.
Yeah, I hope, yeah,
okay.
So that people who are joining via Zoom can also follow, hopefully. So basically what I would like to do today is to tell you a little bit about what this whole paradigm of local operations and shared randomness is, when it becomes relevant, and how is that connected to the question of quantifying non-classicality. And there we go. So let's kind of see these three things that were in the title of the talk, which are this concept of quantifying things, the concept of non-classicality, and the concept of local operations and shared randomness. So these are three things that I will give you a slight introduction to quite briefly. And we're going to start with, operations and what shared local operations and shared randomness is. Then we're going to move on to the types of non-classicality that I want to tell you about today. And then towards the end of the talk, we will finally discuss the whole question of quantifying non-classicality. And this talk is based on 3 articles that I have with colleagues. One, this one here, the first one is about, actually I have a pointer, there we go. The first one is about non-classicality in Bell scenarios. The second one is about non-classicality in entanglement experiments. And the third one is non-classicality in EPR steering experiments. Hopefully, which I will give you a very brief introduction to shortly. So, like I said, we are going to start with operations. So let me go there first. And by the way, I really want this to be an interactive talk. So if anyone from the audience wants to say something or ask a question, and here as well, in the physical audience here, please join the discussion. So, operations, quantum or classical. So what is kind of the idea that or the way that I will use this word during this talk? Well, usually if you have, say, a quantum system, say it could be a quantum system of dimension 2, maybe let's just say this is a Hilbert space of dimension 2, so it's it's just a qubit. And that can be, for example, prepared in a particular quantum state. This is density matrix rho. And of course, I am running out of space at the top. So now the question is, what kind of operations can we do to this system? And operations that we can do are this, lambda operations, which are usually in the quantum jargon considered to be completely positive and trace preserving maps. So this is a completely positive and trace preserving. And let me just, for preempting things in the future, make these quantum systems very, very big. And well, this CPTP map lambda could potentially, change the dimension of the quantum system that we have inputted in it. So this, at the end of the day, we can have some whatever output quantum system coming out of it. And examples of this could be, say, a quantum channel, thing there, which, for example, can discard the input system and just prepare a quantum system in a particular state. So this, for instance, here, let me maybe choose another color. This thing here would be the inner workings of this this map lambda. Or it could also be the case that, for example, this lambda here, and I lost where I am, there we go. It could also be that this is just a unitary transformation. So here we would have the same dimensions as inputs and outputs. But of course, this is, like kind of like the more general thing that you can do. And here we have just a single system that we're using. But now the question is, can we have like a little bit more structure or richness? And the screen is flickering. There we go. If, for example, we want to get a little more into the structure of what these systems are. And for that, then let's just keep things simple and focus on a bipartite quantum system. And for this case, then, for this particular case, what we will have is, there we go. We'll have two quantum systems, like could be, say, 2 qubits. At some point, it will come back again. There we go. And this could be, initially prepared in some quantum state. And now we want to, act on them via a map. Then now it will have to be a map that maps bipartite systems into bipartite systems, for example, here. And again, this can be, or this will be a completely positive trace preserving map. But the question is, can we do a little bit more? Can we see or think of something like some of the properties that this map can have? And well, there are actually different types of maps that you can consider. You could consider, for example, maps that are just separated. So you have like a local operation, local quantum operation applied to each of the quantum systems. You could also have, for example, another particular type of maps, which is not just this one that I wrote in the left, but it could be, say, a particular, that's supposed to be a particular quantum operation, locally for each of the systems. But this could be, coordinated by some classical variable that is shared. And this would have here a quantum input, a quantum output, a quantum input, and a quantum output. And now becomes relevant because these these thin wires are supposed to represent classical systems and the thick wires, quantum systems. So all of these things here at the left should actually be thick wires.
So lambda denotes the classical parameters which couple both maps?
Yeah, it's like, so lambda could be like a coin that you flip the coin, and the result of that coin flip is that, propagated to both local operations that are acting on their quantum systems, and depending on the value of lambda, then these local operations can vary.
But they can be then classically correlated.
Exactly. So it is like a way to classically correlate the two quantum operations that are being done in each of the.
So lambda is exactly classical communication, no? Or there is some difference?
It's a difference. So hopefully I will get to that in a bit, but this is not classical communication, but it's classical shared randomness. So it's not that like this system, let me take the thing. It's not like this system is forwarding information to this part of the processing, because there's no like wire coming from here to here, but it's just that there is a common cause between those two processes. So that could be something. Then you could also have, you know, something different. Let me find my pen. So, and I was a little bit too enthusiastic. So you could also have, for example, quantum operations that, like before, you could have these two local operations, or I say local, but actually I don't mean local, I mean for each of the systems. I mean, they can be happening at the same lab. But now this could be correlated instead by a, well, classical variable lambda that could have a quantum common cause. So there's like some particular quantum state here, or quantum system that is preparing a state, and that is the thing that influences the two preparations or correlates them in somehow quantumly. And other stuff just for completeness, and this is something that, yeah.
Sorry, so is this an Ensila now? So is there an Ensila to lambda, big lambda 1 and big lambda 2?
Yeah, it's like kind of an external system. For example, it could be a state of a qubit, and that it's that pair of qubits is sent to each of those operations, and those act as ancilas for the individual processing on each of those systems. And then this is a depiction, more like a cartoon, but another possible way of doing this is, say, what you were saying before. So we have these two like individual channels. Here we have our quantum systems. Oops. Here we have our quantum systems again. And what we can have is now classical communication. So there can be things here happening here that can influence this one, and things happening here that then can influence this one. This is not like a formal diagram of any sorts. I lost my pen. Oh, there we are. This is not like a formal diagram of any sort, but it's kind of a way for me to depict, you know, how this could be thought about. So of this here, of all of these things that I have told you about, I want to capture two of them, which are the ones that we might be familiar with and that I'm going to be talking in this talk. So the first one is this case here. And I forgot. Undo. There we go. Let's just write it. So the first one is the one where we have, say, the lambda, that is the lambda 1, the lambda 2, and we have some classical correlation, some classical variable correlating these two processes. So that is one possible way. And the other one is the last one that I mentioned. So the other one is when this channel is, we have the lambda 1, we have the lambda 2, and this could have some classical communication being like fed back and forth between these two different systems. And why do I mention or single out these two in particular? Well, the thing is that this is called, let me draw a line here. This is what is called local operations that share randomness, which is the thing that I defined at the beginning. And this is what you know as local operations and classical communication. So those are the two different ways to visualize what these two things are about. And now, in order to discuss things and hopefully wake you up a bit, let's talk about games. we all like playing games. And what are these games I'm going to try to get you talk about now? So in these games, what we have is like we have Alice and Bob. I drew Alice as a lambda anyways. So we have Alice and Bob, and we have a referee that is the one, you know, coordinating this game. And so that's the referee. Here we have Alice and Bob. And the way that this works is the following. So Alice and Bob share a, or have, you know, as a resource, a quantum state, well, a bipartite quantum system in a particular quantum state. And the referee asks questions to Alice and Bob and obtain answers. So actually, he asks two questions, X and Y, and receives two answers, A and B. So the referee asks X and Y, and the answers that they receive is answers that they receive are A and B. And now, what happens? Well, with all of this table of data that the referee gets, they can get all of this data, these different rounds of X, Y, A, and B, compute the conditional probability distributions, P of A, B given X, Y, and use that to reconstruct by a tomography, because that's what these questions are about, reconstruct or a guess of the state that Alice and Bob have. And now, so far I've just defined these things, but there are lots of things that we still need to settle for this to be a game, otherwise it would be a very boring game. And so the game is defined by an entanglement witness. So the game is defined by an entanglement witness, well, a permission operator. And the goal is that Alice and Bob want to minimize the value of the game, which is here computed as the trace of the witness times the state of the system that they have. So what is then that the referee is trying to capture here? Well, the referee is trying to capture whether there is entanglement or not between the across the partitions of Alice versus Bob. So they want to assess entanglement across the Alice and Bob partition. So now comes the exciting bit that we're going to chat about, which is, can Alice and Bob do something to try to do better at this game?
Convince the referee that they have an entangled state even if they don't have an entangled state, or what's their aim? They want to maximize V raw, but raw is the reconstruction by the referee, or?
So here I think I'm not thinking of Alice and Bob trying to cheat the referee, but rather just they are being honest with the tomography that they do, and what the referee reconstructs is the state that they actually have, so that Here, people are very honest, unlike in real life. But the idea is now whether Alice and Bob can like do something to the quantum system that they have to change the state there is in, if necessary, to try to get a better value at the game. Sorry?
For a particular witness.
Yes, yeah, the game is defined by the witness.
By the way, so what means here to win a game? Who wins against whom?
Well,
So,
Alice,
question, Alice and Bob play together, or they play one Alice against Bob, or together against a friend?
no, it's like a collaborative game.
And you
So,
maximize the score.
yeah, they want to maximize the score that they get.
Together.
Yes. So together in the sense that both of them are in the same lab. So, and the idea is to try to, you know, assess the entanglement between these two different systems that we have, even though
So winning means here optimal strategy.
Yeah, yeah, to try to get a strategy. Oh yeah, I wrote winning, but yeah, no, it's like optimal. Yeah, let me change that with a slightly smaller thing. Yeah, there we go. So this is optimal. So what can Alice and Bob do? Well, either they can just use the state that they have, or they can do some processing of the state to generate a new one that might, you know, be better for them. And now the question is, so they have the state. Oh, I need to change pen. They have the state. And they want to do some processing to construct a new state. And the question is, which processes lambda allows them to do better? And more importantly, which lambda would the referee accept that they use? So these are the, you know, two different questions that we have. And just to maybe give you, there we go. So one possible strategy that you can think of is, well, we have the full set of these bipartite quantum states. So we have all the states. We have the set of states which are not entangled, so they are separable. And then we have the witness that defines the game. So one could always say, oh, look, I should take a parallel line to this one of the witness that intersects the set here in this point. That is rho tilde. And that actually maximizes or minimizes, in this case, the value of the trace of the witness times the state. So
this state is maximally entangled with respect to this witness.
It gives the
minimal value of trace.
Yes, exactly. And so one possible strategy that Alice and Bob can do once they see this is say, oh, that's amazing. I can just take, you know, this lambda to just be, I trace out whatever it is that I had, and I just prepare this, this rho tilde. And that would be this lambda process. Now, the question that I have for you is, would the referee be happy with this?
Alice and Bob sit together in one lab, but they are not constrained.
They are not.
Because otherwise they can't produce every state that is such a lot.
Well, they have the capability of performing this operation. the question is whether the referee would allow them to use that as a potential, as a possible processing of their system, the state of their systems, while trying to optimize the value of this game.
It sounds like cheating. They just create a state for the game.
Yeah, but so that's the question. Do you guys, what do you think? Camille says that they are cheating.
So how they construct this state?
Sorry?
How they construct this state?
They just oh well, they have some machinery where they can prepare the state.
But testing out altogether, what exactly? Could you repeat the process? Where?
So the process is that they have these two systems, and they just discard them. They just take the quantum systems that they have and whatever state it was, and they just throw it in the garbage. And they use whatever quantum setup they have in the lab to prepare from scratch a bipartite quantum state in the particular state that optimizes the value of this game. So Camille said that it sounds like cheating, and I also think that it sounds like cheating because kind of like the referee wouldn't allow them to basically be able to create entanglement if what they want to do is use existing entanglement to try to win the game or to somehow process existing entanglement to optimize the game. So in that sense, then I don't think that the referee would accept this. Wouldn't be happy with Alice and Bob using that processing to try to improve their performance at the game. So what are the kind of things that the referee would allow Alice and Bob to do or to use to try and optimize the value? Well, things that, for example, they could, at the end of the day, what happens is the referee would be happy with local operations and classical communication. So the referee would be okay with local operations and classical communication. Why? Well, because Alice and Bob, they have like a quantum lab thingy, so they could do these local operations that do not create entanglement that are quantum operations, and also chatting to each other to decide what to do or to perform. Maybe like, you know, this lambda 1 and lambda 2 could be like a multi-step process that happens in time. So communicating and adapting and all of this like back and forth of classical information wouldn't create entanglement from scratch. So all of this is something that the referee would be happy for them to use. So one possible option is that they use this. Of course, there are other possible sets of operations that also satisfy these properties that I was telling you, but they like this is one of the most common ones and popular ones that people use, so I thought I would mention it explicitly. So now that we know everything about this game, let's play another one.
So, and what were the assumptions concerning the initial state they are given? Alice and Bob obtained some systems prepared in state law, and we do not know nothing about it. Whether, for instance, how much is entangled, is it entangled at all? Because of course, if it's not entangled, they cannot create entanglement, they will never win.
No, yeah, I mean, if they start with the state that is not entangled,
weakly entangled,
then they can't really do much to try to improve the situation.
So do you make any assumptions in the initial stage?
No, it could be anything. Here, what I was trying to focus is on the discussing how to be careful to choose operations that do not create entanglement when doing processing of the state. In a way, this is supposed to be a very trivial game that I've just presented, because what I want to do is draw a parallel with a more interesting game that I want to present later now. So I was trying just to frame a very, in a way, trivial question with a structure that now I can imitate. So now we have another game. And here we have a referee. We have Alice, again as a lambda. We have Bob. And these are 3 players in the game. And notice how now I put Alice and Bob in different bubbles because they are distant. So they can only perform especially separated actions on their share of the system. They do share, though, a pair of quantum systems that are initiated in a state raw. And it's the same. So now the referee asks Alice a question, Alice responds, asks Bob a question, Bob responds. And like before, with the correlations that the referee observes, they can reconstruct the state that Alice and Bob had. And now we have an entanglement witness. And what we want to do is minimize what we want to do. So the goal of the game is to minimize, again, the trace of, there we go. Actually, that's the value of the game, and we want to minimize it. So let me just delete that. There we go. So just like before, now Alice and Bob might want to do something to their system to try to, try to have a go at improving things or not. So what are the things that you reckon Alice and you can do? I mean, it depends on what resource they started from. Like if they start from a separable state, and the separable state is very, very far away from the hyperplane of the entanglement witness, then there are ways to minimize the figure of merit. It wouldn't go below 0, but you could minimize it by doing some processings, which is also the case in the previous game that we discussed. So the question is, what kind of operations, and I'm checking the time here, I think I'm running out. Oh, okay. So what kind of strategies or things do you think the referee would be happy for Alice and Bob to use to try to get better or to get a better value of this G, which is the value of the game? Classical communication? And why would classical communication be an option?
I mean, just talking to each other shouldn't give you shouldn't give you a
Yeah, talking to each other shouldn't create entanglement, which is what was happening in the previous game. Now, is this game the same one as the previous game? Is definitely not identical. Now Alice and Bob are distant and they perform space-like separated actions. So communicating to each other is not something that they can do. Because they are like, during the in the duration of the experiments, they happen to be outside of each other's past and future light cones, so they are just disconnected. So
they can have the same book.
Same?
Well, book, whatever, the same node, the same.
Yeah.
String.
Sure. Exactly. You were saying something?
No, based on the outcome of rho, they can do an operation which depends on the one.
Yeah, so the idea is in which oh no, those are the previous ones. There we go. So the strategies that Alice and Bob can do, and that the referee wouldn't be unhappy about, basically, are local operations on shared randomness. So they can have, their quantum systems. They have the shared randomness here that not only doesn't create entanglement, but also it could have been shared back upon a time before the beginning of the experiment, when Alice and Bob actually shared like a common past light cone. So this is a LOSR. So what we've seen so far then is that we have two games. So we have game 1 and we have game 2. And here they're both based on an entanglement witness. They both have the same figure of merit. However, and they both want to assess with one or two S's, I don't know, the entanglement across Alice and Bob. So they both want to do the same. However, here the operations that they can do, or that the referee allows them to do, is LOCC, and here is LOSR. So we can see that the particular way in which the experiment is set up, even if they have the same, they're defined with the same parameter, they assess the same value of the game, they want to assess the same physical property that underlies, here the entanglement between Alice and Bob. Nonetheless, we can have different types of processing allowed, and that is because of other extra ingredients that the physical scenario has, and that is not part of the definition of what the games are, or it doesn't come across in how the value of the game is computed. And this is, I think, kind of like one of the main things that I wanted to bring your attention on before, hopefully in a few minutes, I can tell you about the rest. So I think that's kind of the key idea so far. So now we've talked about operations and how they arise naturally as objects of study in different circumstances. And then we're going to talk about non-classicality. And hopefully this is going to be, this is something that we're kind of more used to about talking about. So it will be a little bit more dynamic. Let's put it that way. So oh no, I missed a slide. There we go. So the three types of non-classical phenomena that I want to tell you about very briefly now are Bell non-classicality, Einstein-Podolsky-Rosen steering, and also revisit this entanglement where we have a separated Alice and Bob. And for Bell non-classicality there, and see how I say non-classicality, and I will avoid using the term non-locality. And this is actually from before I met Marek Żukowski. So there were like independent reasons that people choose not to use the word non-locality, and we can talk about later if you want. So here, then what we have is we have Alice, we have Bob, we have Alice, we have Bob. There is kind of a system that is prepared, sent to both Alice and Bob, and then Alice can perform measurements on her system. You know, the classical label X denotes the choice of measurement, and then we have A, not B, I'm getting ahead of myself. The classical label that denotes the outcome of the measurement that Alice has performed, and then Bob also performs a measurement and obtains an outcome. And these are the choices of measurements here. These are the choices of outcomes. And then the object of study that they have here is this probability, conditional probability distribution of obtaining AB, given that they've chosen to measure XY. And here Alice and Bob in the Bell scenario are space-like separated. So they might share a classical, they might share a common cause that might be classical, quantum, or whatever, from when they used to have a common past light cone. But during the duration of the experiment, they are in like space-like separated regions. And from a game perspective, how does it look? Well, we have the referee, we have Alice, we have Bob. Referee asks a question to Alice and obtains a reply. And I keep writing B. And we have Y, and there's a B there. And the referee with this computes the probability distribution, the conditional one. And then the way that the game works is by just, you can evaluate the functional related to a Bell inequality, which is given by, you know, coefficients A, B, X, Y. And so the value of the game then would be the sum over A, B, X, Y of the C, A, B, X, Y, and then we have the probabilities A, B, X, Y. And the game is then defined by the choice of the Bell inequality, so the coefficients, and the goal for Alice and Bob is to maximize the value of this G. And whereabouts am I? There we go. Now, EPR steering is something similar. So we have here Alice and Bob. Alice has a black box, and you know, she can put an input and give an output, and Bob does nothing. So basically there is this source that prepares the system, sends it to Alice and sends it to Bob, and Bob just has the system, and they are space-like separated as well. And here then basically this is what is called a steering scenario, and we have this space-like separation and so on. So it's kind of a relaxation of a Bell scenario, because now Bob doesn't have a black box, so we actually trust everything he does in his lab, and we can characterize, or he can characterize, the state of the quantum system that he has in hand. And from a game point of view, this is what is usually referred to as an extended non-local game. So we have the referee, we have Alice, we have Bob, and the referee asks a question and obtains an answer. And then in each round, Bob just sends the state. And here then, the referee then gets the value of X, A, and then the particular quantum state that Bob sent him in that round. And from here, basically the object of study are these conditionally prepared states or conditional states, which are given by the probability of A given X times the normalized state that Bob sent to the referee. And here then what we have is we can define the game in terms of a steering inequality, which is like a Bell inequality, but now we have operators rather than coefficients. Okay, so we have that, which is the steering inequality. And so now the value of the game, or the thing that Alice and Bob want to optimize is, AX is this. And we have f of a given x, and a comma x, and sigma of a given x, and we take the trace. And that is the figure of merit that they want to tackle in this particular game. And well, for the entanglement one, you've already seen it because it's what I talked about before. So, no, this was it. That was all right. So that I've told you about before. So now we know what are the three scenarios and how they are, the operations that arise in each of them, and the three scenarios for non-classical phenomena. So now, what are the strategies for the games that we can have? Well, if we have a Bell scenario where we have, Alice and Bob and their devices, this is Alice and Bob, then if they want to improve or, change the correlations that they share in order to try to improve their performance in the game, then they can't really, do anything apart from local operations and shared randomness, because they cannot communicate to each other, and they also shouldn't share any non-classical resource between them. So basically what a local operations and shared randomness protocol looks like here is like this. So we have a pre and post processes of the inputs and outputs of each of the boxes, and these processings can be correlated by some previously shared classical variable lambda. So here in Bell scenarios we have this, and now in steering scenario, so in an EPR scenario, we have also something similar, because here we have the box of Alice that has a classical input and output, and then we can think of Bob as just a quantum state preparation. And so what we can do is also have, they can't talk to each other, so basically all they can have is a classical shared randomness correlating on the one hand state preparation in Bob's side, and on the other hand a pre and post processing of Alice's inputs and outputs. So those are basically all of the things that you can do for free here, or that you are allowed to do and the referee doesn't complain. So now that we know that, where am I in my notes? We've seen what are the things that are allowed in each of these scenarios as processings of the resources. So now let's quickly chat about the lessons that we learned here. So the first lesson, which is I think the one that I want you to take home today, is that it pertains to the anomalies of non-locality. So what does this mean? So basically an anomaly of non-locality is something when you say, oh, we have a particular property of some non-classical phenomena that can be achieved with a partially entangled state, but not with a maximally entangled state. And from the point of view of what we were doing here, this could be thought of as a box. Oops, let me get black. This can be thought of as a box that has inputs and outputs. And And this box, we can think of it as arising from Alice and Bob performing measurements on a shared entangled quantum state, or a shared quantum state. And now the thing that people have noticed is, in this particular example of one of these anomalies, is that there exists a box that can arise from a partially entangled state psi, but no from the maximally entangled state. And why is that interesting? Well, why is this puzzling? Well, the thing is that we have, on the one hand, let's just write these three things down. We have our maximally entangled state, we have our partial entangled state, and we have our box. And we see, well, a maximally entangled state can always transform into a partially entangled state. And the partially entangled state can be used to generate the box. So by transitivity, one could just start from the maximally entangled state and end in the box. So why? So this is, a conclusion from transitivity. But the fact is that this is actually not happening, and that's a fact. So how can we make sense of this? And the idea is that, from what I've been telling you so far, you should kind of see it from this plot, that when we see that this partially entangled state maps into this box, we're assessing it with respect to local operations and shared randomness, because that's basically what you're doing. We have this partially entangled state, and you're reaching actually only local operations. You don't need shared randomness here to create the box B. However, the protocols to go from the maximally entangled state to a partially entangled state are about local operations and classical communication. So the transitivity argument doesn't really follow here, because we are assessing these conversions with respect to a different set of operations. And that's why, at the end, this is not a puzzling physical effect, but rather just a bookkeeping mistake. Yeah.
So by LOCC, you know that you can go for maximally entangled because you since your interpretation compensation.
Yeah, exactly.
Is this kind of transition condition derived for LOSR? Do you know what, like, if I'm given no?
That's what I'm going to tell you in the next slide. Okay. So it's a very interesting thing, Camille. So this is just a bookkeeping mistake. So we've learned that lesson, that we need to be consistent with what we're doing. And now that we know that we need to be very careful, then we can start a formal pathway to characterizing resources in, say, here, entanglement scenario, well, entanglement with distant party scenarios, or Bell scenarios, or EPR scenarios, and now tackle quantification of resources and transformations. So I'm not going to get into the details of any of that, but what I'm going to tell you are three cute little things. So these three cute little things are the following. So this would be for Bell. It would be a very big eraser there. So for Bell, it would be for EPR and for entanglement. So the thing is that in each of these scenarios that I've been telling you about, you can define a set of resources. So you can define, say, entangled states parameterized by a theta. You can define assemblages parameterized by a theta, or you can create boxes. All of these are recipes that I can tell you about later if you're interested. And the thing is that here, from an analytical method, we showed that all of these states are incomparable under LOSR. So let me just put an LOSR here. So what we refer to as a maximally entangled state is no longer maximally entangled if you think of it from the point of view of LOSR transformations. So here there does not exist maximally entangled state.
But there still is some for every pure state.
Every pure state, as long as it's not separable, is
good in its own way.
Better than every other in some way. So you can find a particular way in which this state that is not the singlet is much better than the singlet, and you cannot do anything to the singlet so that it would be as good as the other one.
Even if the state is very, very weakly entangled, it's epsilon to the boundary.
As long as it's not separable, then you can do it. And also for,
So this one is as so for each type of LOSR operation, there exists a maximal resource.
No, so
for each game.
So for each entangled state that is not the singlet, pure entangled state that is not the singlet, you can find the game such that that particular pure entangled state performs better than what the singlet could ever do.
Local operation.
No, I mean like a Bell inequality sort of thing.
Game is like maximize trace or
I mean, for example, remember in the first case that we had the same game, it was the entanglement witness, and that we had the same figure of merit because it traces W times rho. And we wanted to assess the entanglement between Alice and Bob, but depending on whether Alice and Bob were space-like separated or not, then they could either use LOSR or LOCC. So if they are not space-like separated and you can use LOCC, then you can always go from like the maximally entangled state to any other state. However, if you are in the situation where they are separate, space-like separated, then all of these pure entangled quantum states are all different. Yeah, and the same thing happens here. So here we found like an infinite family of monotones, which are kind of they are like a figure of merit that you can construct from steering inequalities, and you can also see that all of those all of the assemblages in this family theta here are incomparable, which means that there is no such a thing as a maximally non-classical assemblage. And finally, the same goes for Bell scenarios. Here only with two monotones, so with two figures of merit that you construct from many inequalities, monotones. You can also prove that this family of infinite boxes in a Bell scenario, they're all incomparable, and so that there is no such a thing as a maximally non-classical box. And this is because also here we are talking about, we're restricting ourselves to quantum resources. We're not thinking of pure boxes or anything, because then the situation would change. But this is just for quantum things. And now, thanks for the patience and for the patience as well, and with all of the technical details. So this is a summary of what I've tried to tell you. Something that I forgot to tell you, which the thing is in the summary, is that we also developed linear programs to tell whether a box can be converted into another one. So that's a single instance of a linear program, which is great. And for the case of assemblages, it's a semi-definite program. So it's also really good because you can implement it in your computer. So as far as Bell and EPR is concerned, if you give me two boxes or two assemblages, I can tell you whether one can be converted to the other one by LOSR. And things that I didn't tell you is that all of these concepts and tools can actually be straightforwardly applied to multipartite scenarios, even though I've only talked about Alice and Bob here. And finally, the other thing that I didn't tell you about, but that we can talk about later, just drop me a line if you are in the Zoom audience, is that with all of this discussion that we've had today, we can motivate a new way to define what genuinely multipartite non-classicality is. So genuinely multipartite entanglement, genuinely multipartite non-classicality, etc. So thank you. I'm sorry for that.
Joe, can you see me? Yeah. Yes. So we start discussion. Maybe it will be easier first to ask you from the audience, but to make sure that other people can hear you, and you can come here and show your face and ask questions. So who would like to ask? Let's go there, and then they will see.
So yeah, I guess the microphone is good now. So you said, can you go one slide before? Just one slide.
Yeah.
So you phrase this result, the three ones, as there is no maximal. Okay, there are two different things. One is the maximal element, like the best maximal entangled state, and the other is you said that that there is no order at all, right? Because those are two different things. So
yeah.
So I just wanted to ask whether there really is no order. So basically, going from LOCC to LOSR, you destroy this beautiful meteorization order and say like there's no order. Every state is good.
So what you have in these situations is that you have different resources, and like some of them, for example, here the top row are all maximally non-classical in whatever way they want, and they cannot be interconverted into each other. But for example, this one could be converted there, that could be converted there.
Yeah. So there is some partial structure.
Yeah, there is a partial structure, but there is not like unique structure.
And this partial
not a total order.
This partial structure, you don't have an explicit analytical thing, but you have a program, a linear program that decide what. Okay.
Yeah.
Thanks.
Good. Thank you. Further questions? Perhaps are there any questions from the remote audience? Please check. Who would like to pose a question? Yes, so.
So if I understand correctly, this diagram you drew is for the non-separable states. But is there any like order to, like, for example, can separable states be interconverted?
What?
Yeah.
No,
the non.
Okay, separate ones. Yeah. So basically, you can always, so in any of this, regardless of whether it's entanglement or steering or non-classicality, you can always go from one free resource, which is, a like separable state or a local box, to another one, another separable state or a classical box via LOSR operation. So there is like all the set of classical resources for each of the scenarios forms a unique equivalence class. So having one particular classical box is equally as useful as having another particular classical box.
So I guess you can always discard and create a new one.
Something really weird happened to the boundary then.
So, maybe one more question. Last question. Maybe I will ask a simple one concerning this. At the very end, you talk about those genuinely entangled multipartite states. Yes. So, what is the difference with respect to this previous, let's say, standard notion of multipartite, genuine multipartite entanglement?
So let me try to add a page. There we go. So, I mean, very shortly, the idea is that if you have a say, just to keep it simple, a tripartite quantum state. So the usual notion is that it's genuine multipartite if there does not exist a bipartition of the three systems, such that the row can be explained as a kind of row 1 and a row 2, or like convex combinations of this sort of thing. So that is the usual notion. The notion that we would try to push for is that what you want, so this is that is genuinely multipartite if you cannot express it in terms of local operations and shared bipartite entanglement. So what does it mean? That you have here the three parties, Alice, Bob, and Charlie, and you can have like some classical three-way classical randomness, and you can have like a quantum state for Alice and Bob, and you can have a quantum state for Bob and Charlie, and you can have a quantum state for Alice and Charlie. But as long as you can use this bipartite entanglement, this goes then with these two go up, that's the quantum state, the quantum system, sorry, and all of these then go, that's the quantum system for Alice. So as long as this ABC here, which is what I obtained here at the end of this process, if this cannot be explained like this, so if there's no bipartite quantum states and tripartite classical randomness that generates it, then it is multipartite entanglement.
Okay. Thank you very much. So there are no further questions.